So we finished section 1 revision. Now to we will continue section 2, but I can break something here because this was the last title we talk about section 1. It is about how angular rotation quantities of rotating object is changing or not changing, same or not same for different points. And finally, we set down for any rigid object, rotating rigid object. As this object is rotating, every single part, any single point on this rotating object will turn the same angle. We have angular displacement that's going to be the same for every single point. And angular acceleration is going to be the same for every single point. And angular speed is going to be the same for every single point for a rigid rotating object. We stop it here. Then from this point on, we will continue section 2. But if a point or an object has a different angular speed than another point, in this case, we cannot say this object is to be rigid. This must be, shape should be changing, and it is going to be a non-rigid object. So the object is non-rigid. We expect the points to have different angular speeds, different angular displacement, different angular accelerations. Now, from this point on, we will continue with section 2. In section 2, we are going to compare linear quantities. We are going to study linear quantities. Because object is moving in a circular path, as an object is moving in a circular path, we can also measure its motion by linear quantities. This section talks about that. So carousel. Carousel is a rigid object. So there are two horses on the carousel, A and B. As these two horses, when the carousel rotates, these two horses also move in a circular path. And because carousel is a rigid object, both horses will turn the same angle. And their angular displacements are going to be the same, just as we said at the end of section 1. But if we want to measure this circular motion of these two horses by linear quantities, like distance, like linear speed, like linear acceleration, we are going to observe that these quantities are different for two horses at different distances. Look at this picture. Horse A and horse B, they are moving at different distances. Because horse A travels a shorter distance than horse B. Horse B travels at the longer distance. Even though they have the same angular displacement, outside horse travels a longer distance than inside horse, which tells you that outside horse has a greater arc length than inside horse. Even though they have the same angular speed, they have the same angular displacement. Their arc lengths and distance traveled by these two horses are not the same. So then we say that outside horses always travel longer distance than inside horse, which tells you that in terms of linear speed, in terms of the speed which is going to be studied by the distance, outside horse must be faster than inside horse, and then we are going to say that. So this linear speed, which is in a circular motion, is named as tangential speed, and outside horse is going to have a greater tangential speed than inside horse because it travels a longer distance than the inside one. So then, the linear speed in circular motion is given a name. That name is tangential speed. Definition of the tangential speed is, it is instantaneous linear speed of the object along the circular motion. Yeah, we are going to talk about circular motion. If we are defining tangential speed, object should be moving in a circular path. At least a part of the path must be a circle, a part of the circle. So it is instantaneous linear speed because it is defined from position to position. Every different position can have a different tangential speed. That's why it is instantaneous. Linear speed, yes, it is because it is defined in terms of distance. And object must be moving in a circular path. Only for circular motion you define tangential speed. And tangential as a word talks about the direction. Tangential means angle to tangent. Because if I draw a tangent line at this point, at this position to these circles, these tangent lines are going to show us in which direction these forces are moving at that moment, at that instant. So, tangential, their direction of motion are going to be tangent to the circle at those points. For example, when the horse comes in here, if I want to know the direction of the motion, I have to draw a tangent line. So direction of the tangent line will tell us in which direction this horse is moving. Then, why is it called instantaneous? Maybe you get the idea. Because even though they can have the same speed, directions are different. So in here different, in here different. That's why it's instantaneous. Yani direction is continuously changing in a circular path. That's why this speed is tangential, is the instantaneous linear speed. And outside horse travels a longer distance than the inside. That's why outside horse must have a greater tangential speed than inside one, which tells you the tangential speed is directly proportional to distance from the axis of rotation. What we named is radius. Yani, if the circle has a greater radius, tangential speed must be greater. If the circle has a smaller radius, it should have smaller. Why? Because angular speeds are the same, tangential speeds are different at different circles. And the equation of the tangential speed can be obtained by using the relation between angular displacement and angular arc. Angular displacement arc divided by r. Cross product, delta s equal r delta theta. When you divide both sides by delta t, you can. We are going to get delta s over delta t, distance divided by time. What is distance divided by time? Linear speed. And that linear speed in circular path is called tangential speed. Tangential speed is equal to r delta theta over delta t, and delta theta over delta t is what? Angular speed. And this equation also tells you that why outside horse has a greater tangential speed. Why? Because r and tangential speed are directly proportional, because omega is the same for these two horses, because concentration is check. So as r increases, tangential speed should increase. This is just we said at the beginning of this section. And this is how tangential speed and angular speed are related. So that for a rigid object, two horses at different distances, which one has a greater tangential speed? Outside. Why? Because it is a greater radius. The outside horse is a greater radius of the circle. Okay. What if this carousel is speeding up from speed to another speed? In this case, we are going to calculate acceleration. If an object is speeding up or slowing down, we calculate an acceleration. One of the accelerations we calculate in section 1. If you are defining the motion of object in the circular path in terms of angle, angular speed is increasing or decreasing. And we calculate angular acceleration. But this time we are going to define one more acceleration again for circular motion. But this time we are going to define this acceleration in terms of distance, yeah, the linear acceleration. So as this carousel is speeding up from an initial angular speed to a final angular speed, absolutely we can calculate angular acceleration by which equation? Alpha is equal to omega final minus omega initial divided by delta t. But if initial angular speed is changing from initial value to a final value, absolutely tangential speed should be changing too, because they are directly proportional. So remember the equation, E is equal to R times omega. If there's a change in tangential speed, angular speed, there must be a change in tangential speed as well. Then tangential speed should be changing from initial value to a final value. And if there's a change in tangential speed, it's a linear speed. If there's a change in linear speed, in the 11th grade you calculate it the same way we will calculate again. So if linear speed is changing, there must be a linear acceleration. And how we are going to calculate this linear acceleration is going to be final linear acceleration, linear speed minus initial linear speed divided by delta t. In fact, equation is not very, it's not new. What was acceleration equation in the 11th grade? The final minus the initial divided by delta t. So this is now only, instead of linear speed, we are going to say tangential speed, final tangential speed minus final initial tangential speed divided by delta t, the same way we calculate angular acceleration. So when cursor speed swap with a constant angular acceleration alpha, the horse also accelerates from initial tangential speed to a final tangential speed. Along the circular path, the horse experiences an instantaneous linear acceleration, which is named as acceleration, linear acceleration in circular path, named as tangential acceleration, short definition. But common definition of the tangential acceleration, in fact, very similar to the tangential speed. It is instantaneous again, from position to position. This direction is changing, direction of the tangential acceleration is changing. So this one is instantaneous. It's in linear because you measure in terms of meter per second squared. Acceleration of an object must move in a circular path. Again, tangential acceleration is going to be tangent to the circle, directed tangent to the circle, and it is going to be found the same way we calculated the linear acceleration. Any linear acceleration, what was that? Delta V over delta T. How it is VT only? Changing tangential speed, then we find. Look at this equation, which is the common acceleration of the linear acceleration last year we studied. From this acceleration, I can get the, at the same time, definition divided by delta T, which was rate. The rate of change of what? What is changing? Tangential speed. The rate of change of tangential speed in tangential direction is called tangential acceleration, and this is how we calculated it in the 11th grade. We can still calculate this way, but in the 11th grade, in the 12th grade book, this equation, there's no question given with this equation. So we just relate, I'll find angular acceleration and tangential acceleration. From this equation, we can continue. I know that delta Vt over delta T, and we know Vt is equal to what? R times? Omega, right? Delta Vt means R times delta omega. So I'm going to try for delta Vt R times delta omega. Delta omega over delta T, what did we name in section 1? Alpha. So this is what the equation is. At is equal to R times alpha, and tangential acceleration is changing almost the same way how tangential speed and angular speed changes. You should multiply the angular acceleration by radius of the circle, that you will get tangential acceleration. It also says that if there are two horses at two different distances in a carousel, outside horse must have a greater tangential acceleration because R greater AT. Inside horse will have a smaller tangential acceleration. Okay. And also, tangential acceleration and angular acceleration are directly proportional, even they have the same sign. If one of them is negative, the other one is negative. If one of them is positive, the other one is positive. Yani, in the case of speeding up, so both are positive. In the case of slowing down, both are negative. In the case of constant speed, both are zero. Okay. And this is the summary. Yes, if you multiply rotational quantities by radius of the circular path, you are going to calculate corresponding linear quantities. Angular displacement times r plane. Angular speed times r, tangential speed. Angular acceleration times radius of the circle, which is equal to tangential acceleration. Okay. And another acceleration. So alpha, angular acceleration, and tangential acceleration are related. They're related by an equation. At is equal to r times omega. Because both are due to the change in the speed. Yani speeding up or slowing down case in a circular path. Both are calculated because of that reason. Alpha and AT. Both are calculated because of the speeding up in a circular path or slowing down in a circular path. That's why they're related by equation. But there is one more acceleration. Centripetal acceleration. Centripetal acceleration is because of change in direction of the motion of an object as object is moving in a circular path. When this horse is moving a circular path, its direction of the motion is continuously changing. This direction change also gives an acceleration to this horse. So, by changing magnetic velocity, we calculated tangential acceleration in numbers. But by changing direction of the motion, we are going to calculate a new type of acceleration, which is going to be named as what? Centripetal acceleration. Yes. Consider a car is moving a circular path with constant tangential speed. If tangential speed is constant, absolutely AT is 0. So, this is tangential speed, this is tangential speed, this is tangential speed. When this car is moving from one position to another position, direction is changing, so vector is changing, velocity is changing, tangential velocity is changing. Tangential speed constant, but tangential velocity is changing. Why? Velocity is a vector, quantity direction is changing. So because of this change, we can calculate an acceleration. But to get this acceleration, first we should draw delta V. Delta V is what? So we final minus, we initial final tangential speed minus initial tangential, velocity, better say tangential speeds are same, but velocities are not same. So tangential speeds are same number, but directions are different, which makes tangential velocity different. So this tangential velocity and that tangential velocity are different. Why? Because their directions are different. Then if there's a difference in the tangential velocity, we should be able to calculate a delta V, yani changing tangential velocity. This delta V is not very difficult to find. We are going to find it just like how we find delta X. Put these two vectors side by side so that their tails coincide from the tip of the initial vector to the tip of the final vector, throw an arrow. This arrow is going to represent changing tangential velocity, delta V, pointing in the center of the circle. Delta V is pointing in the center of the circle. And according to acceleration equation, delta V and acceleration all the time in the same direction. Sometimes students get confused with this. Delta V and V are not same. V is velocity, but delta V, change in velocity. A velocity is tangent to the circle, but delta V is not tangent to the circle. What is the direction of delta V? Delta V towards the center of the circle. They are different. Okay, so because delta V and AC are in the same direction, so they are going to both are pointing in the center of the circle. But while VT is tangent, delta V towards the center, so AC towards the center. This acceleration is called centripetal because its direction is pointing the center of the circular path. Then, this acceleration is named as centripetal acceleration because its direction towards the center of the circle at any instant. But tangential acceleration is, tangential speed is tangent to the circle, tangential velocity tangent to the circle, but AC is towards the center of the circle. What about delta V? Also towards the center of the circle. Centripetal acceleration AC is itself a vector. Yes, as you see, it has a direction, and its direction is continuously changing too. AC direction is also changing. Sometimes you say, teacher, towards the center, towards the center, towards the center, but in which direction? We don't need to find the direction this way. To the left, to the right, up, down. So, arrow directions continuously changing according to your page. So it's like tangential, centripetal acceleration is continuously changing in direction, so it's a vector. It is not constant too. It's not constant. To say constant AC, direction must be all the time in one direction, but it's not. So, centripetal acceleration itself is a vector and its direction is continuously changing. This is why we cannot say that AC is constant. AC is not constant due to direction change. Centripetal acceleration AC and velocity perpendicular to each other. Yes, tangential velocity is tangent to the circle. AC is towards the center of the circle. Angle between VT and AC is how much? 90 degrees. One of them is tangential, the other one is towards the center of the circular path along the radius. And delta V also pointing towards the center. Yes, delta V, AC towards the center, but VT is tangent to the circle. Tangential velocities. Tangent to the circle, delta V is towards the center of the circle, AC is towards the center of the circle. And AC is calculated depending on how quick the direction changes. A quicker direction change produces a greater centripetal acceleration. A slower direction change produces a smaller centripetal acceleration. So then, direction changes. If object moves faster, direction change becomes quicker, which tells you that as speed increases, AC should increase. Yes, and it depends on how quickly object moves in a circular path, how quick the direction of the velocity changes. So that's why definition of the centripetal acceleration is going to be time rate of change of what direction? Time rate of duration of the direction is how quickly the direction is changing. When an object moves in a circular path is called as centripetal acceleration. And equations, as I said, as speed increases, direction change becomes quicker, yani AC increases. Yes, look at these two equations. AC, VT is in numerator, omega is also in numerator, yani increasing tangential speed or increasing angular speed, both causes increasing centripetal acceleration. Both are squared. In here was squared, in here is was squared. But in this equation, it's V squared over R. R is in denominator, but in here R is in numerator. It's about which speed you are going to keep same for two objects when you compare their ACs. For example, in here, if you are going to compare AC of two objects must have the same tangential speed. Then AC and R inversely proportional. Also makes sense. Why? Two different circles. If two car moves in these two different circles with the same tangential speed, say that 5 and 5, which one changes direction quicker? Of course, small one changes direction quicker. Yeah. R is smaller, AC is greater, but what did we keep the same? VT. If you keep VT same for two objects which are in a circular path, AC and R are going to be inversely proportional. But second equation is not about this. Second equation, you should keep which speed the same? Omega. Omega is the same for two objects on a rigid object. Remember, two horses on a rigid object. So in this example, for example, carousel. In the carousel, omegas are same every point. There are two horses. One of them is inside, the other one is outside at A and B. This is the axis of rotation. They have the same omega, correct? But R's are different. Which one is the smaller R? Inside. Which one is the greater R? Outside. Which horse will have greater centripetal acceleration? The one on the outside, because R is greater. Longer, greater R, greater AC. Yeah, these two equations are talking about different cases. In one of them, for two objects moving a circular path, VT must be the same, AC and R direct, inversely proportional. But in here, two objects have the same omega, AC and R directly proportional. Okay. And centripetal acceleration is a linear quantity because you measure it by meter per second squared. Yes?
Teacher, if it says the VT is different, we have to use the second equation?
The case must be set to. For example, two automobiles moving in two different circles. And so this is independent paths. So then if the tangential speed is kept the same for both, so AC and R,
inverse.
But if they say you, yeah, they're independent, but we are going to keep omega the same. In this case, you should use this equation. Yani, which speed is kept the same for both objects or two objects? Then according to that case, you have to decide. You have to use this one to comparison, or you have to use that one for comparison. Okay? If they say we are keeping tangential speed same for both, you should use for this equation for comparison. Or if they say to you, we keep angular speed same for both to compare, so you have to use this equation. Okay? And of course, what if both happens at the same time? What does it mean? There is speeding up or slowing down at the same time direction change. If car is accelerated from rest to another speed, as you see 0, 10, 20, 30, it's speeding up, so you are going to calculate absolutely tangential acceleration. Yani magnitude of velocity is changing, directional velocity also changing. In this case, we are going to calculate two accelerations. Tangential acceleration, it's going to be because of the speeding up or slowing down in a circular path. It is tangent to the circle. Second one is centripetal acceleration due to direction change. When we draw them on the same circle, because both are acceleration, same type of the quantity, we can add them. To calculate what? Total acceleration. So AT and AC are going to be added and we will find total acceleration. AC and AT always perpendicular. Because AT is tangential to the circle. AC is radial on the radius. So angle between tangent and radius is 90 degrees. So if two vectors are 90 degrees, we can add them by Pythagorean, which is equal to AC squared plus AT squared square root. This is the equation how we calculate total acceleration. And one more thing, angle. This angle can be calculated too. What is this angle? In fact, it is the angle between total acceleration and directional velocity, and in which direction the car moves. This angle is theta. How can we calculate it? By using sine theta, cosine theta, tangent theta, one of them. Tangent theta is the best to calculate this angle. Tangent theta is in this right angle triangle, opposite perpendicular leg, which is AC, divided by adjacent perpendicular leg, which is AT. If we divide AC by AT, we calculate tangent theta. When we inverse it, we are going to get how much is the angle between directional velocity and total acceleration. And as you see, this theta depends on not only AC, not only AT, both of them. And summary. This tells you that there are two different nature of accelerations. One of them is, one nature is because of the speeding up or slowing down. Tangential acceleration and angular acceleration, they have the same nature, that's why they are related by an equation. AT is equal to R times alpha. But second one is another nature because of the direction change, which we said as centripetal acceleration. And then these two different nature of accelerations combined, we calculate total acceleration by this equation, x squared plus AT squared. You can insert a different version of these equations. You can write a different version of this equation by inserting AC and AT in different form. And uniform circular motion, we define that. What is uniform circular motion? If an object moves in a circular path with constant tangential speed, this motion is called as uniform circular motion. If tangential speed is constant, what does it mean? AT must be equal to 0. But AC can never be 0 in circular motion because direction continuously changes. In circular motion, AC never 0. That's why in total acceleration, you are going to write AT 0, which tells you that in uniform circular motion, A total is equal to only AC.